is to have some sort of continuity with what we've been talking about in terms of decision analysis. So decision analysis, as we've discussed a few times, is axiomatic. So many things that we do in engineering and mathematics, we first decide what are the set of axioms that we want to follow. These are rules that we all agree are true and apply, even though they cannot be proven, right? So these are something that are taken as facts. So, um, so for example, you can't be at two places at the same time. So here we have an example of a person who can't be in the US and Europe at the same time. And then the benefit of this approach is that it helps us come up with methods to make decisions. It helps defend decisions. So if you make a bad decision or say that somebody that made a decision is bad, then that can be shown to violate one of the axioms. And then this approach to making decisions was presented by von Neumann and Morgenstern in 1944 in their book, um, Theory of Games and Economic Behavior. So, and over the years, we'll see many people talking about these axioms in one way or the other. For example, Savage presented his own way of these decision-making axioms. You'll find it in different books. It's basically the same general idea, except that people are interpreting it differently, presenting it differently, and which makes um, in terms of the maximum expected utility criterion that results from it. So if you believe in these axioms, you will actually end up with the idea that all rational decision makers tend to maximize the expectation of their utility function when they're making a decision. And these axioms will lead to that. So in this lecture, we will mostly discuss the axioms presented by Howard, which are the 5 rules of actional thought. So I will quickly go over some of these slides because we don't want to be too repetitive. So the 5 axioms we've been talking about, or we will talk about rather, is that order rule, probability rule, equivalence rule, substitution rule, and choice rule. So order rule basically states that when we're dealing with deterministic outcomes, we can rank them in the order of our preference, right? So on the left here, we have a bunch of outcomes, let's say A, B, C, D, E. These could be money outcomes. This could be, the type of car you end up with, type of design you end up with. You basically can say that, A could be preferred to B, B and C are the same, C is preferred to D, and D is preferred to E, or any other choice of out or ranking that you prefer. Okay, so of course, notation can be self-evident sometimes it's not. So the idea is to stay internally consistent. So we see that generally people very easily agree with the order rule, so we won't spend too much time talking about this. The preferences must be transitive, means that you can't have cycles. So if you say A is preferred to B, which is the same as C, which is preferred to D and E, then E now you can't come back and say E is preferred to A. That is not allowed. Okay. All right. So, and the probability rule again is stating that a decision maker can assign a probability to an outcome based on their degree of belief. So, for an event that they have data on, or the event that they don't have data on, based on their degree of belief, they can assign a probability to the likelihood of an event, right? So this is, like I said, it's informed by prior information and data. And we will skip this again because we have already talked about this earlier. And finally, the equivalence rule. Now things are getting a little serious, right? So now we say that we have a sure outcome on the left-hand side, which is in this case B. We can just call it $10. It doesn't have to be money. It could be any other attribute. And on the right-hand side, you have some distribution over the outcomes, right? So you have a lottery where with probability P, you get the best outcome, and then probability 1 minus P, you get the worst outcome, right? So the idea is that you can always find an equivalence point between option 1 and 2. So in this case, a decision maker would say that for some specific probability value or value of P, they can they can say that option 2 and option 1 are equivalent. So of course, P has to exist, because if P was 1, you would prefer option 2. If P was 0, you'd prefer option 1. So an indifference point has to exist. And we sometimes call it the preference probability associated with the, let me just see if I can move this out of the way, associated with the outcome B. So this probability that makes you indifferent between an intermediate outcome and a lottery between the best and the worst outcomes is called the preference probability associated with the outcome on the left-hand side. In this case, it is B. All right, so we talked about this. Won't spend too much time on this. And then, okay, and now finally, substitution rule states that if you say things are equivalent, then you should have no problems replacing it. So here let's say we had some decision which gives you an outcome B with probability Q and outcome D with probability 1 minus Q. Now notice that B and D are intermediate outcomes. We will replace B with its own lottery between the best and the worst, and D with its own lottery between the best and the worst, and these probabilities will be different because B and D are different options. We can do some calculations and say that this original lottery can be converted to this binary lottery between the best and the worst outcomes, right? And then these probabilities can be derived. So for this example, we can keep going and say that now we are ready to use the final axiom, or the choice rule, which says that, well, number one, all uncertain lotteries can be reduced to a binary lotteries between best and worst that we already saw. The choice rule states that once we have done that, once we have converted them to binary lotteries between best and the worst, we should, or the rational decision makers should, select the one that has the highest probability associated with the best outcome. So, so option 1 here could be some complex decision involving many outcomes. We can do the calculation and end up with this option, which is just a binary lottery between A and E. And in our example, what we've been doing is that we've been calling A the best and E the worst, for some probability, let's say 0.6 and 0.4. Option 2 could be some other alternative, which has, once you do the calculations, you may end up with, again, the best and worst in this fashion. And now, since everything is the same, the outcomes are the same, the lottery structure is the same, obviously you should prefer option 2 because it has the higher probability associated with the better outcome, or the best outcome in this case. So this is sort of saying that once you follow the first 5 rules or first 4 rules of decision analysis, then you pretty much have converted all problems to the simple decision problem where the choice is trivial. Now, what do we gain from something like this? We gain a lot. We say that 5 rules are enough to make decisions under uncertainty. You don't need anything else. These will help you structure any decision problem in a standardized way, and you can use them to make decisions. So how could I use the 5 rules to make decisions? In the case of small number of discrete alternatives, let's say if you're choosing between a few different alternatives, let's say a few cars or a few houses to buy or a few sample designs to select from, that's pretty trivial. In that case, you would simply use the 5 rules directly. You'll follow through the, what is your ranking of outcomes, what are the probabilities you assign to each event, and then you do the substitution, equivalence substitution, then you make the decision directly, and it's pretty straightforward at that point. On the other hand, you could use the maximum expected utility criterion. Okay, so maximum expected utility criterion is a more efficient way, mathematically sound way of implementing the 5 rules of decision making, or the axioms that we all agree on. And in the next lecture, we will use this method for conceptual selection. Actually, it may actually end up happening in the same lecture itself. Okay, so any questions so far?
It is okay, clear enough.
Everything's clear, right? Okay,
Yes.
great. So, right, so we'll go to the utility functions. So now we'll change gears here, right? So we'll talk about utility functions because we already said that our 5 rules or 5 axioms of decision making imply a maximum expected utility criterion of making decisions. We'll talk about certainty equivalent, which is an important concept in decision making. And then we'll talk about value of information and then multi-attribute decision making. So we obviously have learned about the axioms of decision analysis in our various discussions so far. Looks like students agree that those are valid assumptions, valid axioms that we can found the theory of decision analysis on. Now, we talked about utility functions. Let's expand on that concept, right? So the thing that we're especially looking for are that how to make decisions using utility functions and how to assess the functional forms of utility functions. So the first line basically says that if you had a utility function given to you, and sometimes that happens, right? For a given decision problem, a utility function is known either for the individual or group of individuals or a an organization. There's obviously the jury is still out whether we can use utility functions for multiple decision makers to find a combined utility function. But let's say that utility function already exists, then we should know how to use that utility function in a generic decision problem to make decisions. That's one. And then how to assess functional forms of utility function. So let's say utility function was not given to you for a decision maker. How do you assess it? What kind of questions you can ask to assess the functional form of the utility function. So for later decisions, you could use those. Okay, so let's go back to what we've been talking about when we talked about the preference probability concept. And we'll revisit the same example where you have 5 different amounts of money, 5, 15, 25, 50, and $100. And then you rank them in this order, right? So 100 is better than 50, which is better than 25, which is better than 15, which is better than 5. So, and again, I like to reiterate every time we do this, is that this is just a mental aid. This is not something that we necessarily have to do. These could be pets, for example. These could be cars. These could be designs. These could be any outcomes that you can rank. Okay. So, and then you assign, or you basically, yeah, assign the preference order for those outcomes. So, with that being said, if let's say a decision maker says that this is true, that they are indifferent, so you see the indifference sign here, between $50, which is one of the intermediate outcomes, and a lottery between the best and the worst outcome with some probability distribution, right? So they provided this number to us, the decision maker does. And when they provide this number to us, we can say that the the preference probability for $50 is 0.8, and we can repeat the process for all the other amounts. So we can repeat the process for $25, we can repeat the process for $15, we can repeat the process for $5. And let's say a decision maker provided these values. They don't have to, but they did. The thing that we have to just be careful of here is that whatever order is presented here should match the order of these numbers, because if something is more preferable, then you will assign a higher probability to the best outcome associated for this lottery. So okay, so let's go. So we have 150, 25, 15, 5, 1.8.5.30. It follows the same order as the preference for these numbers. And again, these could be any outcomes that don't have to necessarily be money. Okay, so now what we do is that the utility value we assign to an outcome is the same as the preference probability of the outcome. So now we say, okay, let's think of a function. Let's envision a function that takes values that equal the preference probabilities associated with the outcome that the decision maker provided. So we can just write it as simply as u of outcome. So utility function for evaluated it for a given outcome. So now we just follow the same process, right? We say preference probability of 100 is 1. preference probability of utility of 100 is also 1, and so on and so forth. So these numbers are the same. We're just saying that now here's a function utility that takes these values. Okay, so pretty straightforward at this point. Nothing magical done here, except that now we're starting to get an idea of what we can do with this knowledge. Okay, so let's try to solve a problem. Very simple problem. Okay, so everybody knows by now the standard representations in a decision tree. So this is a decision where you choose between two alternatives, A and B. You have an uncertain outcome. You have 0.6 and 0.4 probabilities for either getting 50 and 15. And right away we see that this decision cannot be made in an ad hoc way, or at least should not be made in an ad hoc way, because while A can result in a high outcome of 50, it can also result in a low outcome of 15. B gives you a static fixed 25 every single time. And different people, based on their different preferences, will make different decisions in each case. So with this knowledge, we replace, hang on if I can somehow, okay. This is better, actually, you can please see people. Okay, so what we did is that we replaced the utility, replaced the outcomes with the utility value. So we, instead of 50, now we try 0.8. So A outcome will give point with 0.6 probability, something with utility of 0.8. And then it can also give an outcome with 0.4 probability, something with utility of 0.3. And now the decision is trivial, right? So we said that we find the expected utility of option A. The expected utility is pretty straightforward. This is just a discrete probability distribution with two outcomes. The expectation would be 0.6 times 0.8 plus 0.4 times 0.3, and you get 0.6. And option B is 0.5. So we will select A because it has higher expected utility. So as you saw, it was a pretty easy process. It was an easy process because obviously the mechanics of decision making are embedded in the utility function, but it's also an easy process because it was a very simple decision problem. So nothing difficult here, but we at least starting to get used to the idea of how to make decisions under uncertainty using the expected utility criterion. Now, if we actually plot the numbers that we had, we start seeing a trend. So on the x-axis, you have money, which is went from $5 to $100, and then associated utility or preference probability values, which went from 0 to 1. And then when we plot the utility function, we start getting an idea, oh, hang on a second, we can actually fit a functional form to this. Right? So if you find the equation for this curve, we can interpolate and extrapolate utility values for all realistic outcomes. So initially we assess, I mean, there's some design of experiments going on here, right? So if you know what's the range of negotiability is, which means that the lowest amount that somebody will accept and the maximum amount at which, or the maximum amount that is considered reasonable, we say utility here is 0, utility here is 1. And now we can interpolate and extrapolate if we are able to assess the utility values at enough number of points. So the design of experiments concept here is that obviously for a single attribute is not as difficult, but still this should be a well-distributed collection of points. So we did one at 15, we did one at 25, and then so on and so forth. So now we have a few points and we can interpolate and extrapolate for other realistic outcomes. So we're not stuck to only knowing the utilities of these points. We know the utilities for all the points between 5 and 100. Okay. So, and then we don't have to acquire an additional preference probabilities for this. So long as we stay close to the points. I mean, of course, we cannot go much beyond this. We can't say what is the utility of 120. In fact, since we said 100 has the highest utility, we won't be doing that anyway. Okay, so now we did that because we want to solve problems that are extensions of the simple problem that we solved earlier. So here, if you look to the outcomes, they are different from the amounts that we assess the utility for. So now the decision maker can actually leave the room because we got what we wanted out of them about their decision-making preferences. So the decision problem again would be considered one of the simpler problems. You're choosing between alternative A and alternative B. Both are uncertain, and here's the probabilities, and here's the outcomes that we already talked about. But what's helping us here is that we have a utility function that helps us solve this problem. So I can leave that to the students to solve, or we can come back to it. It's up to them. But the main point that we're trying to address here is that we're trying to fit a utility function, right? So a couple of things are essential before we start. We need to know the range of negotiability, and this is defined by the upper and lower limit of the attribute. For example, money doesn't have to be. The decision maker is actively considering. So this is a very interesting concept because, of course, more is always better for certain attributes, or less is always better for certain attributes, right? But we define a range where things are feasible, we expect things to happen. And what it does is that it limits the discourse to only the things that are reasonable. And we don't talk about really large values, really huge amounts of torque in an engine, or very high fuel economy. Those kinds of things would be good to have, but we know they're not reasonable. And then if you use a really wide range of negotiability, you may not be able to do very good analysis. The other thing is important in addition to range of negotiability is preference order for an attribute, right? So does the decision maker prefer more of an attribute or less of it? Or sometimes a nominal value is better. So this is easy. You can convert that still to a deviation from the nominal value. So you can still have convert a problem where you have non-monotonic preferences to a problem with monotonic preferences. So for example, for electric bill that you get for using appliances at home, I am actively considering values between $0 and $250, and lower is better, right? So, and these are actual values for me. I mean, I would say my electric bill will never be more than $250 in the foreseeable future, and it's never, it probably will never be zero either. But then this is a good range of negotiability, and I prefer it to be as low as possible, right? So that's my preference order. Fuel economy for a vehicle, at least for a gasoline vehicle, I would say 20 to 50 is the range of negotiability, and higher is better. So I want higher fuel economy to lower. Now, the thing to understand here is that lower than 20 miles per gallon does happen. So it's not just a matter of is it feasible or not. We do have large SUVs which give lower than 20 miles per gallon fuel economy, but I'm not actively considering those. For me, this is the lowest I will accept, and this is the most I expect. And again, these numbers are informed by what we call meta-analysis, right? You think about your decision problem before you go around making decisions. That what have I seen? How can I use my personal experience in life and having seen cars and having driven cars, having read about cars, what are these numbers that should be? And then this step often is overlooked. And that's when a lot of problems start, because if our modeling step is poorly done, then we will not be able to make good decisions. So 20 miles per gallon is the lowest I would accept, and 50 miles per gallon is the largest fuel economy that I expect. I know that a lot of sedans that are hybrid sedans will maybe reach this under certain conditions. Okay, so those are the two concepts. And then we have to choose the correct functional form. So for utility functions, most common ones that you would see are exponential, linear, logarithmic, and polynomial. For this class, since this is a condensed class, we will limit ourselves to exponential function. And that's also the most prevalent for multiple reasons, which we will talk about in a bit. So this looks complicated, but it actually isn't. When you prefer more of an attribute, u of x is this expression. So you can pretty much ignore the denominator. If you look at the denominator, it is just a normalizing constant, right? So since x max is known and x min is known, all this turns out to be a constant if r is also known. We'll get to that in a second. And here we just say that, your utility function is increasing. If x increases, you have two negative signs here, so u of x also increases. And then here, if you prefer less of an attribute, you have 1 minus e to the negative this. Here we just reverse the order here. Normalizing constant stays the same, which basically says that if x increases, then the utility decreases. So x max and x min are the lower and upper limits, x min and x max, I should say, of the range of negotiability, and r is the risk tolerance to be found. So we don't know that yet. We will find it. And it's easy to see that once we do this normalization, the utility function is going to be between 0 and 1, which is something we want. So that we always like to have that correspondence between, like, that utilities is a probability. So when we said, we assign the utility function the values that are the same as the preference probabilities, that concept actually helps. In fact, if you follow research in decision analysis, many people have actually made further, more theoretical connections between the utility functions and the CDFs of random variables. Okay, so let's do an example. So here's the utility function that we had, preference probability values and utility values. So in this case, our range of negotiability is 5 to 100, and we prefer more money to less. So the functional form we will choose is this one. So this is the more is better functional form. You can, from a mathematical sense, you can say this is an increasing function in x, and it lies between 0 and 1 for these values. So it will go above and below 0 and 1 if you exceed this range. So it's only defined, or we try to only define it between these ranges. Okay, so the only parameter we know is we need to know is the value of r, right? So we use an Excel routine to find a good value, right? So since this is just a single attribute problem, we can do it visually. So utility input are these diamonds here, and then we select the value of r that makes sure the function crosses this, or is the points are equally distributed by the function, pretty basic curve fitting, and then that gives us this utility function, right? So you'll see once r is known, this is just a normalizing factor, it's a constant. The only thing that changes here is x, right? So there is a Excel file that I have offered to students in case they want it. I can show it to you briefly, what it looks like. So and this is something that, again, like I said, if you want access to it, you can email me, or you can create your own. Nothing really difficult about this. So basically, you have two types of attribute: more is better or less is better. And then in each case, you have the attributes. So these could be fuel economy, these could be any other attribute, weight of a vehicle, or the maximum stress that a component can take, and so on and so forth. We have inputs, and then we basically, this is just set up so it tells you, okay, well, this is the problem you're solving because you understand decision analysis now, and then x min, x max are known. So just select an r that fits these points well. So if I had used, let's say, a 20 here, and then we see that it makes the utility function more concave, which means the decision maker becomes more risk averse. We can address those things later in the lecture. If you make it, if this number is really large, then you become more and more risk neutral. The function will become less and less concave. So if I use a really large number, you see it becomes almost linear, and so on and so forth. So I think 31 seems to be the good fit for this. This is a simple problem. There's nothing really hard here, but the idea is that you're doing some sort of curve fitting. If you were getting a utility function that you cannot fit using exponential, then you would look at logarithmic or in a more general case, a polynomial utility function. And we've used those in some of our decisions where we felt that the exponential was not covering the things well. But for the most part, it works for decision problems. One thing to note here is that no matter how large the R value is, it will never become convex. So it will always be for risk-seeking decision makers, right? And then another thing, I mean, I don't know if we'll get to this in this class, is that there's an interpretation for R. It's called risk tolerance. For certain specifically defined lotteries, it measures your indifference point. So without getting too much into it, the larger the number, the more tolerant to risk you are for that particular attribute. Okay, so we'll come back here, and then so there you have it. Right, so now we're ready to solve this problem, right? So remember this number we didn't evaluate. The decision maker is no longer in the room. We can just use their utility function to make this decision. Okay, great. So what we do is that we replace these outcomes with their utility values. We have the function, so now we can actually plug in the utility values here. So 0.6 times 0.741, 0.4 times 0.581 gives you 0.68. And similarly for the other branch of the other alternative. So here we see that the given utility function or the decision maker with these set of preferences will select A over B. Now, personally, I felt like this was not a decision I could have made trivially. So if I just look at this decision problem, I'm thinking, okay, 30% chance of a really high outcome, 60% chance of 43, 40. Yeah, this looks mostly like, I'm pretty safe. My range of outcomes I'm going to get is between 30 and 43. I look here, oh, it's a wider range. I'm undecided. But if you come here, you certainly see that the decision was not even close. And that's an important point to make here, that since utility functions are concave, higher values don't affect the utility that much. In other words, the marginal improvement beyond a certain point is not that much. Another way to see this is that once you go from 80 to 100, you only increase by 0.044, as you can see here. So the utility function not so much penalizes higher values, it just stops valuing it as much for every increment. Okay, so to keep our promise here that we can make a concept selection decision using decision analysis, right? So the framework is pretty straightforward. So throughout this class, we were working with a Venturi scrubber, and we will use decision analysis to select the best Venturi design. So assume that we only are working with single attribute problems. We'll talk about multiple attribute problems later in the lecture. The objective we're considering is the negative pressure generated. So we assume that the lower and upper limits are 5 inches of water column of pressure and 9 inches of water column of pressure, right? So this is our range of negotiability. We will not accept less than 5, and we don't anticipate it being more than 9. And we want to maximize this attribute. So we want higher the better. The closer you are to 9 inches of negative pressure, the better it is for us. Okay, so we would have problems like this in engineering, where you would say, okay, well, should you select a design? And this is, again, hinting to a really large field of engineering, which is design and uncertainty, where you make engineering decisions when you have uncertainty in outcomes, whether because of material properties or manufacturing processes or any other, or environmental variables or user inputs. So this kind of stuff is pretty common. So venturi that provides a negative pressure of 7 inches with 0.8 probability and 5.5 inches with 0.2 probability, or this other alternative design, okay, so, which also has an uncertain um, performance. So the first step would be to find the utility function for this attribute. Let's say we asked a decision maker, and we have the handy dandy Excel file. So we just plug these attribute values. We say the 5 is 0 because that's the worst outcome. 9 is 1, which is the best outcome. And then the intermediate ones, we ask the decision maker, what is the preference probability? So you obviously know the trick. You say, okay, for 6, what probability of getting 9 versus 1 minus p probability of getting 5 would 6 be equivalent to? And you say 0.7. So just refreshing in our minds that 6 having a preference probability input of 0.7 means that the decision maker is indifferent between 6 and a lottery that gives 9 with 0.7 probability and 5 with 0.3 probability. So we repeat the process, and then we go through the Excel file, and then we find the best fit utility function. So again, we find that in this particular case, we found that the utility function exponential seemed like a decent fit. The decision maker is risk averse because it's a concave utility function. Of course, if we wanted, we could use a more general functional form in this case as well. Okay, so if we stick to the exponential, this is the utility function that we found. The risk tolerance is 1.2, and then rest is just all known quantities, and then we go from there. So if we had to make that decision that we talked about a couple of slides ago, we have 80% probability of 7, 20% probability of 5.5. We replace with their utility values. Now, the good thing about this example is that we're not using money, but the same concept holds. So the utility, either you could end up with 0.8411 with 80% probability, or 0.3533 with 0.2 probability. And similarly for the alternative design, right? So the idea here is that, let's say you had a Venturi scrubber, and we can think back to our concept generation and how to design systems and so on and so forth. And we say, okay, well, we could use a Venturi, or we could use something else. If all else remained the same, which is almost never the case, but then you would say, you know what, I can evaluate it using my this utility function approach that I found, and then I'll say that I can make a decision in this fashion. Now, one thing to note here is that we've been saying that range of negotiability definition is important. So here, if you remember, we did not assess the utility function beyond 9, okay? But if the alternative design gives you 10, that's not really a benefit to you, because you're what we call a diminishing returns property of the utility function. Make sure that you really don't care once the pressure is over 9. So you still assign a utility of 1. So this benefit is not really worth it to you. And that's exactly what the kind of things that the utility function captures. Okay, so we just go through the calculation steps. The expected utility from using the Venturi is 0.8 times 0.8411 plus 0.2 times 0.3533 equals 0.74. Expected utility from the alternative design is 0.7. So based on the expected utility criterion and the design alternatives we had and the preferences of the decision maker, we should select the Venturi over the alternative design. Okay. So this is also probably giving you an idea of how to proceed in this fashion, and then actually start using utility analysis in comparing engineering designs with uncertain performance. So this is, relatively speaking, a new field. There was quite a bit of effort put into bringing the knowledge of decision analysis into engineering design, system design decisions in the late 80s, 90s, and even early 2000s. So now you're equipped to do something like this. And are there any questions from our participants?
No, I think it is pretty simple, easy. Yeah, easy to follow.
Yep. Okay, great. So that's how we like it at this point. So now we can get into the little bit into the utility function itself, and then talk about the idea of certainty equivalent. So we know from Jensen's inequality that for a concave function, a function that has this shape, for a single attribute function, you'll say that it's a function with a negative second derivative if it is differentiable, twice differentiable, that is. The expectation of the function is always less than the function at the expectation of the argument. So we can understand it pretty trivially here. If we say, let's say we have two outcomes, x1 and x2, and then you had a lottery between them, 50% lottery. So let's say 50% chance of getting x1, 50% chance of getting x2. So the expectation of this random variable on the x-axis, whose realizations we see, is the midpoint, right? Because it's the 50% point. And then we project that up, and then we say, oh, the utility function at the expectation of this is this value, u of expectation of x. On the other hand, if we reverse the process and we found the expectation of the utility function itself, which means that for x1 and x2, we had the utility values, and then we looked at the 50% point on the y-axis, then this will be the expectation of the utility. So we see that the expectation of the utility function is less than the utility function evaluated at the expectation of the outcomes. Another way to think about this is this is the behavior of risk-averse decision makers. For risk-seeking decision makers, this will be reversed. The expectation of the utility function will be higher than the utility function expected at the expectation of the random variable. Okay, so let me just move this out of the way. This is what we call, so if we project this back, so we found the expected utility, and then we project it back to the x-axis, we find what's called the certainty equivalent. Okay, it's a very important concept, and certainty equivalent, as you see, is less than the expectation of the outcome. Another way to say it is that risk-averse decision makers are called risk-averse because they value uncertain things less than they would value certain things. Okay, so and then that's a pretty commonly observed trait. People who are most people are risk averse, at least in for reasonable numbers. I mean, sometimes people argue that we are risk seeking for really small amounts, or at least risk neutral, and we start becoming risk averse for larger and larger amounts. The concept of diminishing returns takes over. But either way, for most decision makers, we see this effect that certainty equivalent is less than the expectation. But we should not assume it. We should always verify using calculations and assessments of their preferences. Okay, so just to get the definition out of the way, so certainty equivalent is the sure amount which is as desirable as an uncertain lottery or decision to a decision maker. Okay, so it's useful to decide whether to undertake a risky decision, and this is something that we'll think about quite a bit in our engineering practice, that oftentimes we have a design that we understand, and then we're trying to explore, should we look for something new? Should we look for something which has uncertain performance, right? And well, we sometimes have to map that back. How much is that uncertainty in certain terms? What certain design I can give up, what fixed design I can give up to get to compensate for the fact that the new design or the alternative design has uncertainty. So in some ways, we have already seen this. When we find the preference probability of an intermediate outcome when we're fitting utility functions, we've already seen this, right? When we say what makes you indifferent. So here's the same problem flipped. Earlier, we were giving an option here or an outcome here, and we're saying what probability makes you indifferent. Well, here we're saying, okay, fix the probabilities. What option makes you indifferent? And this is very important because even though you would say there's the same way of thinking about things, but once you get this concept that we can leave anything out, there's many ways to assess preferences. Okay, so we could, and this could also be used to fit a utility function. You just have your equations will be different and your approach will be different, but you'll get the same general result. And sometimes it's a good idea to ask the same questions many different ways so that we get a good handle on the exact utility function that the decision maker is using. So whatever number you provide for this lottery, whatever you say here makes you indifferent between option 1 and option 2, and that would be called a certainty equivalent of the lottery on the right-hand side. So this is a decision problem on the right now. That's why everything is known. Well, I guess not everything is known in decision problem. So let's say a decision problem where you know the probabilities and know the outcomes. You can now assign a fixed outcome that will be as desirable as that. Okay, so just as an aside, this was for 0 to 60 acceleration times of cars, right? So we can start changing the attributes and decision problems to make a decision. So if you had a choice between, let's say, 3 seconds would be Formula One type times, and this is your still a decent sedan. What car has the same, what acceleration rather for a vehicle has the same utility to you, and then you go from there. Okay, so now this is just a simple lottery, and then it's easy to understand. But when you go into decision problems like this, you can now talk about certainty equivalence of the entire decision. So the thing to what we're trying to extend here is that you can say you may have one decision that if I go there, I'll make a decision and I'll make another decision. I'll make another follow-up decision. Once you go through these decisions, you will eventually end up with a utility. And that utility will be sum total of your decisions, the uncertainties, the outcomes that you have. But you can still assign to all this a certainty equivalent value. This whole thing has a certain certainty equivalent. Of course, to do that, we first need to solve the decision tree. You need to know what you would have done if you had this decision to make. So let me see if I can move this. Yes. All right. So slightly more complicated still, not very complicated, but you have two uncertain outcomes for two uncertain alternatives, four outcomes for alternative E, two outcomes for alternative F, and they're both uncertain. The numbers are, you can obviously read it off the slide. So what we do is that since we were given the utility function, we will replace these outcomes with their utilities. I hope I haven't made any calculation mistakes here, but these are the numbers that I think we have. If you wanted to use or truncate this, you could do that, but we're just trying to show you how this process will work out. So we find the expected utility of branch E, which comes out to all these calculations and comes out to 0.07597. The expected utility of branch F, which comes out to all this and 0.0972. Great. So now it's trivial to say that you will prefer F over E, right? Higher expected utility. Now we can say that the entire decision has this utility, okay? So even though decisions were involved, since you are a rational decision maker, since you use a utility function that is known, we know what will happen if we went through these steps. And this is an important point. I mean, I could add multiple steps beyond this, right? And some of the steps will depend on how other uncertainties resolve themselves and so on and so forth. Whatever, even if it's a complex decision tree, your overall utility can be found. So your expected utility of the entire decision is 0.0972 because that is what you would choose if you solve the decision tree. Now we can find the certainty equivalent, right? So we just invert the utility function, and we know that at least in this case, our utility function is invertible. So we would solve what value of x for this decision maker gives me that utility. Okay, so we go through the process and we find x equals 30.67. So 30.67 is the certainty equivalent of the decision, means that I am indifferent if, let's say, these were money amounts that were given to me, or these were miles per gallon of radically new design that we had. I guess miles per gallon could not be negative, but any attribute for that matter, right? I could say all this decision, and I have a competing decision that has a value of 30.67, I'll be indifferent. So that's the indifference point for the entire decision. That's what certainty equivalent measures. So another way to say this is you would give up the uncertain decision of playing the tree and just take 30.67 units without any change in satisfaction level. Or if you have 30.67 units, you will exchange it with the tree without any change in your satisfaction level. So that's the indifference point. Okay, so I think I will leave these to the students if they want to find a certainty equivalence for these utility functions. They're not necessarily normalized, so we can ignore the fact that you're getting numbers that are above 1 or below 0. In fact, scaling utility functions is not a problem when you're solving decision trees. If you scale them using a positive number or add a constant to it, you will still make the same decision. So if they're so that's not a problem. Just the thing to see here that this on the top you have a linear utility function which points to a risk neutral decision maker, and here you have a convex utility function points to a risk seeking decision maker. Easy stuff. So now this leads us to the next concept, which is also a very important concept, which is what we call the value of information. Okay, so the idea behind using utility functions is to be able to make decisions under uncertainty. Okay, we want to be able to do that. It's a really powerful tool. We should be able to make decisions under uncertainty. But just because we can do that does not mean we have to contend with uncertainty in our decisions. We all know that we can mitigate uncertainty through data collection or getting expert opinion. So there are many examples of real life decisions where you would first collect data and reduce uncertainty before you acted, right? So so that's when decision analysis helps us again, that we have a way to find how much we should pay for that information. And then we can talk about all sorts of things. What if the information is perfect, and what if the information is imperfect? What if the information is incorrect or malicious, right? So there's ways we can deal with perfect information. There's ways we can deal with imperfect information. Malicious information, it can be harmful, and we really don't know unless we know what is the likelihood of the information being malicious. Okay, so right, so we all know how to make a decision using the maximum expected utility criterion. It's been shown to be pretty straightforward. You have two alternatives, A and B. B is certain, A is uncertain. Everything is pretty straightforward at this point. Okay, so now we made the decision, and we decide that since A has a higher expected utility, we select A. Okay, so there you go. We made the decision. Now, let's say we have, and this is a concept that we use in decision analysis sometimes. Let's say you have access to the services of a clairvoyant who can tell you what will happen if you selected A. In other words, earlier you were saying, if I go with A, I could get this or I could get that. No, now clairvoyant says, if you went with A, you will get this. Or they might say you will get that. So are we in a better situation now? Let me engage my audience here so that it's not just one person talking.
Sure. So, based on this, for sure, I would pick go with A with higher utility function.
Right, but if somebody came and told you that I can tell you that which way A will resolve. So A, when you select A, you're accepting uncertainty, right? That you might get 200 with 0.7 probability, you might get 10 with 30% probability. In which case you will have some regret if you went with A, knowing that on an average case from an expectation standpoint you were doing better, but you may end up with a worse option. You're not getting 50, you're getting, let me just move this out of the way again. You could have gotten 50 if you just went with A. So there's regret associated with it. If you go here, of course you're happy. So somebody tells you that information before you play the lottery or make the decision. Are you better off?
Oh yes, yeah.
How so?
Certainty will clear at least information ahead. We have the information ahead of what to expect.
Right. But they don't tell you before they. So let's say, of course, they're going to charge you money, right? So
Yeah.
They don't tell you before they charge you money. So would you pay them?
Then it would be what is the other option? So it depends on what is the other option that I have. Cost to the option that is left.
Right. So yeah. So the thing is that first we all agree that if at this stage, so this is as we say, you start with the left side and this is how it progresses in real life. At this stage, somebody tells you that I can tell you how A will work out, but you have to pay me money now. That's going to require some calculations. And one of the reasons we started with the axioms, one of the reasons we go this utility function route is we can do things like that. In fact, there's other ways to make decisions in engineering. There's AHP, there's weight and rate type methods, there's a whole bunch of methods that are not founded on mathematics where you couldn't do that. But here we can actually calculate exactly how much we should pay them. Okay, based on our preferences and based on our based on the probabilities listed here. In fact, so much so that we can find the maximum we should pay them, not and also if their information was uncertain, we could also extend this concept to value of imperfect information and so on and so forth. This happens all the time in engineering. So when you are prospecting and you try to find out whether a certain oil well has any oil in it, you pay somebody to do the logging. Of course, you have to have some idea of what the likelihood of the event is, but you still pay somebody to find the information. You pay for tests, right? So non-destructive testing is one of the things we do in engineering. And non-destructive tests, of course, cost money. And we don't know if there's, let's say, a beam or a machine element has a crack in it or has an internal, let's say, issue. So when you do those kinds of things, you are actually doing value of information, how much you should pay them. And of course, you should not pay more than it is worth, right? So knowing the maximum amount is very critical. And yes, we will pay the information provider. So yes, so we're better off, and then we can see how we're better off, right? So we'll have to bring the uncertain node to the beginning of the decision tree. Okay, so we said, okay, first, the clairvoyant tells how A will resolve itself, whether you will get 200 or 10, and then you make the decision, right? So that's where the the value, I guess, of the information comes in. That if you know this information, you will say, of course, I'll go with A because I'm going to get 200. And the clairvoyant is always right. We in this case, we're assuming perfect information, so they're always right. Versus when the clairvoyant says you will go with, if you went with A, you will get $10. Well, then you'll go with B, right? So the value is coming from the fact that you're never selecting the worst option in this case. And of course, the extensions exist to this problem, imperfect information, like I said, or if these probability distributions were continuous distributions, we could still do a similar kind of analysis and that wouldn't be a problem. So yeah, of course. So I never end up with 10, which is the worst outcome in this case, without, well, I never end up with 10 in this case if I went with the clairvoyant, right? So that's where the value comes in. Now, how do you calculate that value? We'll go with this in this case, and we'll go with that in the second case. Okay, so now another question here is that can the clairvoyant change the future?
It can make it better because we are avoiding the worst situation. So it can only make it better, but not. Maybe if I don't listen to the clairvoyant, then there is a chance that I could either hit the worst or the best.
Right, right. So in some ways, so basically from the event that they're telling you information about, they cannot change the future, right? They cannot. A has a probability distribution associated with it, 200 or 10. They cannot change that. They can just tell you what will happen, right? So another way to think about it is like if there's a crack present inside a beam and you're using some X-ray techniques and you're paying this company to tell you whether there's a crack present, they cannot make the crack go away. They cannot change the probability of the crack being there. They can just tell you that it's there or not if you paid them money, right? After that, you make a different decision. So they, in some sense, they change the future because they can change your probability of choosing A or B. But the event itself for which they're providing information, they don't change the probability. Do you agree?
Yes,
No?
totally. Yes, totally.
Yeah. So, so if the clairvoyant is always right, now that's another thing that I wish we had time to talk about imperfect information as well, because that's pretty much what we see in engineering, right? When we do oil well logging or when we do any type of um, engineering design, we have not only the fact that we have continuous distributions, we have many kinds of distributions, we have joint distributions, all those things that we have to worry about from a probability theory standpoint, but then also the information is imperfect, right? So they may miss something, whatever tests that they have, like when you do a medical test, that's the same thing, value of information, right? You pay to get a medical test done. They don't change the fact that somebody has high blood pressure or low blood pressure. They don't change the fact that somebody has a certain disease. They just tell you. And then you can now, but the thing is that that knowledge helps you, so you pay for that knowledge. But they don't change the probability of the event. Um, and the other thing with real life is that the information is imperfect in real life more often than not. But that's okay. We just work with, a few nodes get added to this when we talk about what is the probability of them saying that something is present, what is the likelihood of them being right, what is the likelihood of them being wrong. In other words, if they say a crack is present, what is the likelihood of the crack present? If they say crack is not present in a beam, what is the probability that the crack is not present? And vice versa. When they say yes, the answer could be no. When they say no, the answer could be yes, and all those combinations. So it gets complicated very quickly, but the framework is the same that you're learning here. So here, one thing that's very easy is that we can just write these probabilities. These were the probabilities of A resulting in 200 or 10. Okay, so we just move it directly here because the clairvoyant is always right. So you have perfect information. If they have perfect information, then probability is what you get. Okay, so 0.7 probability that you'll get between no 0.7 probability that if you went with A, you'll get 200. Well, of course you'll select that. And 0.3 probability that if you went with A again, you'll only end up with 10. Then of course you won't select that, and you will select the $50 choice, which is option B. So now we find the expected utility, which comes out to 0.723, which comes out to be greater than the expected utility without information. So information obviously has values. The decision tree shows it. The expected utility value shows it. But we're not surprised anyway because we ran through the mechanics mentally and we say, you know what, we're always avoiding the worst case scenario. So obviously the information has value. Now, how do you find that value, right? So to find the maximum you would pay, and this is again, it's the maximum amount. It's not the amount you should always pay. That maximum amount will equate the expected utility with perfect information with the expected utility without information. So let's say we play the clairvoyant X dollars, right? So sometimes we'll have to do some fancy calculations, but nothing too difficult. So we just change the decision problem in this way. Since you have paid them, you pay them regardless of what they tell you, right? It's because you have to pay them up front. And then there's a whole bunch of regret, right? Why did we hire this company to tell us if there's oil or not? Because no oil came out and so on and so on. But at least they saved you one way or the other. So in each case, no matter what happens, you have already paid them X dollars, okay? And then to find the value of X, we just solve this equation that 0.7 times U of 200 minus X plus 0.3 times U of 50 minus X. So this is pretty straightforward. Utility function is an increasing function. So utility of here, you don't need to actually know the exact utility value to know that this will have a higher utility and this will have a higher utility at the bottom. So you will select this. And then you find the expected utility of the tree with inclusion of the fact that you have paid them X dollars, right? So it's 0.7 times U of 200 minus X plus 0.3 times U of 50 minus X. Writing it out in a more elaborate way and gives you the value of X. Sometimes you have to solve this numerically. Sometimes you can solve it by hand in closed form. It doesn't really matter. You'll find a value of X that is 28 in this case, or whatever it is for your problem. And so then you can obviously, this is just saying in the slide that you can do it manually if you just keep incrementing the value until the sign of the left-hand side changes, or rather left-hand side becomes bigger, and then you can iterate. So if you don't want to solve it analytically, you can, or you can't solve it analytically, you can do it numerically very easily. You can use Excel to verify this answer. This answer is, I think, correct, but if there's a calculation error, that's also an opportunity for you to verify my work. So there you go. That's how you find the maximum value of information you would pay. If somebody comes and says, the clairvoyant in this case comes and says, I want to charge you $35, you say, no, the information is not worth that much to me. If they say it's $5, of course you'll say yes, right? So that's the decision kind of sometimes you have to make in engineering, and we make those decisions all the time. Okay, so that settles that. Okay, so is there anything else I wanted to say about value of information? Oh, yes. So the key to understanding value of information, whether it is perfect or imperfect, is that it's always positive. So we shouldn't have to, so long as it's not a malicious source of information, we shouldn't have to think about like what will happen, what are the outcomes, what are the uncertainties. We say value of information is positive. That's it, right? Because anything that resolves uncertainty has a very good chance of protecting you from the worst outcomes, right? Because you will take the better outcome in each case. So information almost good information, whether perfect or imperfect, always has value. So that's one thing that I wanted to say about that. Switching gears, we're still in the single attribute domain, where we can develop intuition about decision analysis. We learned utility function approaches. They work for multi-attribute decisions as well. We can talk about dominance in single attribute problems. So dominance, whether it's deterministic or stochastic, sometimes helps you make decisions in a simple way. Okay. And oftentimes when I'm teaching this course, whether it's part of systems engineering or in a more elaborate decision analysis class, students will sometimes raise this point like, well, we don't really see deterministic dominance. We don't really see stochastic dominance. But in my engineering practice, over time, I have had a few examples where, what? Deterministic dominance does exist in certain cases. Stochastic dominance does exist in certain cases. So good to know about these concepts. So we say, let's say you have two alternatives or options, A and B. We say that an option A deterministically dominates another option B if the worst outcome of A is still better than the best outcome of B. It means no matter what happens, you will never do worse with A. In fact, you'll always do better with A, because even the worst case scenario of A is better than the best case scenario of B. So in this case, we say A deterministically dominates B. A slight relaxation of that is an option A, again, let's consider the same two options, A and B, stochastically dominates the option if the probability of A giving any amount X or better is higher than that of B for all values of X. Okay. So, so this is slightly more complicated, and obviously it's more likely that you'll have stochastic dominance. So in this case, we don't say that A will always do better than B, but whatever amount you choose, A has a higher probability of doing better than that, right? So we can understand this using cumulative distribution functions of the payoffs. So here we have the CDF of the payoff of A, and more is better in this case, and CDF of the payoff of C, CDF of the payoff of B. So in this case, what do you think dominates what? In fact, these orders are not the same as the previous slide, so let's not stick to the same examples we had in the last slide.
So C dominates B. Because 100% for sure we get the probability by picking $200, and so no outcome would exceed $200. So option C would deterministically dominating C by and B, right? So it is the worst case of 200 is better than the best case of B, that is 350.
So you're saying C dominates B, or B dominates C? So actually, let's go back to the definition of CDF, right? So CDF at this value, let's say 150, says option A has a 50% chance of being less than 150. Okay, 50% chance of it has 100% chance of being less than 200.
200, yeah.
Okay, 100% chance being less than 200, and C and B don't even start there, right? So this is saying that C probability of option C giving less than 200 is 0. The probability of B giving less than 200, even 250, is 0. So we'll say that A is, in this particular case, is obviously the worst.
Yes.
Right? So it's on the left-hand side. If you actually simulated these random variables, inverse CDF method or whatever, you'll get a bunch of realizations here. Okay. Which is saying that sometimes you'll get 100, sometimes you'll get 150, 120, 100, whatever. The realizations will always, for A, will always be in this range. Realizations for C will always be in this range. Realizations for B will always be in this range.
Yes.
Okay.
The
So
worst case
both
of
B and
so when it's here, it shows that the worst case of B is still greater than 50% of option C. So probably option B is better.
right. So A is out.
Yes.
Clearly, right? A is deterministically dominated by both C and B. B and C is not so clear because if and B can result in outcomes here, let's say 225.
Right.
And then C can get lucky and then give you an outcome at 270 or something. But the probabilities are low, right? So we call this stochastic dominance because it's not 100%. It's just that for each value of X, so I put a line here, each value of X, so let's say the number here is 260 or something. Hang on. I messed up earlier. Either way, so you get the point, right? So when I went, this is some number here would be 275, let's say 270 maybe.
Yes.
So C can give close to 300.
Yes.
But it's a low probability event.
The CDF of C is to the left.
Right.
Higher
CDF is the left,
than
and they don't. Yeah, and they do not intersect. So that's another thing that we have to think about, right? Stochastic dominance. Sometimes we talk about orders of stochastic dominance, and then the CDFs intersect. So in this case, they don't intersect for each value of X, for example. So X here is roughly, let's say, 265. B has a probability of a very small probability of giving less than that. But C has a really high probability of giving less than that, right?
Yes.
Another way of thinking that is that B has a high probability of giving more than that, and then C has a low probability of getting more than that. So for each outcome, no matter where I draw this line, B will give more. Sometimes you can work it out in a decision tree as well, that if dominance exists, then you don't have to do any calculations. You can find decisions very, very easily. So deterministic dominance exists, but it's rare. Stochastic dominance exists often enough that it's good to recognize that one option is better than other stochastically, so the decision can be made relatively trivially. Okay, so good. Now we can continue on and talk about the role of experts. So one thing in the entire process of learning decision analysis, obviously, is of academic interest, and it's also something that we can use to make decisions. We can help others to make decisions, but we should never underestimate the role of experts, the domain experts that we encounter in engineering, right? So anybody who's familiar with a decision situation, I keep talking about this. If you've been doing the Venturi scrubber design, somebody's been doing it for 20, 30 years. And that's something I felt when I worked in industry, that they can help better frame decisions. They can say things like, that failure mode doesn't happen, or this likelihood is much less than what you're thinking. Or they can just tell you more things. They're more familiar with outcomes and their likelihood. They can say, okay, this can also happen, which you may not have thought of, right? So one of the examples I remember is we had actually a chemical scrubber, and then we were using certain parts, and they were all compliant with all the design requirements, except that he, from his experience, said that this part overheats, even though you don't think that there's really any heat source nearby, but just from the fluid pressure, this can overheat and get damaged. So use a different part, or something that can handle a higher temperature. So those kinds of things are important. So experts are a great resource in decision making. When we're framing the decision, when we're building the decision tree, we should look at domain experts. They can better frame decisions. They're familiar with outcomes. They can help us assess distributions. They can provide good prior distributions. So many times we don't have data, but they can provide input distribution. They can say, oh, this is beta distributed, we think, with this, or this is the range, or they can give you the most likely value between upper and lower limits, and so on and so forth. So those kinds of things are important. And sometimes they can also talk about things like dominance and stochastic or deterministic dominance, right? So that's the benefit of having decision uh, experts in your decision-making process as you're facilitating decisions.